Hi, and welcome to the Probability and Statistics Tutor. I'm very excited to teach the class because a lot of people over the years have asked me to put this class together, and I finally had the time to do it, so I'm real excited to share it with you today. And what we're going to do is we're going to cover probability first, and we're going to move on into statistics and cover, by and large, most of the topics you'll see in your class, okay? Now, a lot of people have problems with probability and statistics, usually for a couple reasons. The first reason is that every single problem, almost every single problem that you're going to see in this class is basically going to be a word problem. And that just turns a lot of people off from the beginning because instead of just being given a problem to solve in a concrete, rigid way, you first have to read the thing and you have to figure out what it's asking you, pull out the information, figure out how to attack it, and use your logic, what you learn in the class, hopefully, to attack the problem. So what that really means is every problem is different. It's not like, you know, when you were learning your algebra way back a long time ago how to solve an equation. That was new and frightening to you, a long time ago. You got the hang of it because once you learn the rules, it's very mechanical after that for algebra and for calculus and even trigonometry and all this stuff. Once you learn the rules, you just go step by step through them, mechanically turn the crank, and you get your answers out. But in probability, the math is by definition very fuzzy. You usually don't get concrete numbers to everything. You get a probability that something might occur. You're not necessarily going to know if something's going to occur or something's not going to occur, but you're going to get some sort of probability or some number that represents how likely something is to happen. So it's not really that math that we're used to dealing with growing up, that 1 + 1 is 2 and it's always that way. You shuffle a deck of cards, what's the probability you might pull some cards out of the deck? It's not the kind of math that we usually all deal with growing up on a regular basis. So it's new and it's different, and to a lot of people it doesn't seem very rigid and very mechanical once you learn the rules. Well, we're going to change all that, okay? And the way we're going to do it is we're going to start at the beginning, teaching you step by step what every definition means, and working a lot of problems so that you can get your brain wrapped around how to attack these things. So we're going to do it one step at a time. In this section, before we actually get to the probability, you have to start somewhere. You have to start with the foundation. So this section, and actually the next section, doesn't actually have any probability in it. It's laying the foundation for that. Usually when you start your class, one of the first things that you learn about are these things called permutations and combinations. Okay? They're going to be important when we go on and learn about probability and statistics, so we're going to take some time and really understand what they mean. We're going to work a lot of problems. Okay? So what do you think the word permutation means? Okay, I think we've all used the word before. I think you have a basic idea of what it means. A permutation is kind of like an ordering of something. It's a specific order. You may have a red sock, a green sock, and a blue sock. Okay, and that might be a permutation in an order of those socks laid out in your bed. And you might flip it around. You might have a yellow sock, a green sock, and a red sock. It's the same socks, they're just in a different order. Well, that's a different permutation. That's what a permutation is. I want you to burn that in your head. I'm going to say it about 50 times in this section. A permutation is an ordering of events, okay, when the order matters, okay? When the order matters. It's very, very important because in the next section we're going to talk about something else called combinations, where the order doesn't matter. But just put that on your back burner for now. Right now we're talking about permutations where the order does matter. So it's really easiest to understand really what this means if we take an example. So what we're going to do is we're going to run a marathon. Okay, we have 4 people in this marathon and they're running a marathon. So somebody is going to win the race. He's going to be first, or she is going to be first. Then there's going to be a second place winner and a third place winner and a fourth place winner, because in this little example I'm giving you, we only have 4 people. So we're running a marathon, first, second, third, and fourth. What we're going to find out, what we're going to ask ourselves is, if I'm only concerned with first and second place, okay, how many different ways can first and second place occur? That would be basically asking the question, how many permutations are there for the first and second place winners when I have 4 people winning the race? Okay, so let's look at it. So what you're going to have, we're running a marathon, and you're running this marathon, so there's going to be a first place winner, okay, and there's going to be a second place winner. Okay, there's going to be a first place winner and there's going to be a second place winner. And by the way, who is running in this race? Okay, we have 4 people, and their names are Jason, okay, and Sean, and Sally, and Martha. Okay, so all we're trying to do, we're not even doing any math here. We're just talking about a marathon. So we have 4 people, and these people are all running in a race, and on a given day, you know, Jason might win and Sean might be second place, and on another given day, Martha might win first place and Sally might win the second place, and on another day, Sean might win the first place and Sally might win the second place. So every day that you run this marathon, assuming all these people are similar skill levels, some person's going to win the first place and some person's going to win second place. Okay? So what we want to figure out is, of the 4 people, how many different ways can that happen? How many different permutations are there? Because in this problem, the order does matter. First and second place. It obviously matters what order these people come in. That's what a permutation is. I'm trying to repeat it so you get the idea here. So what we're going to do is, instead of just trying to sit on your paper and just try to make up all the different permutations there are, I mean, you could go through this list and you could do your best to write down the number of ways it can happen. The best way to do this, and what you'll see in your book, is to use what's called a tree diagram. Okay, a tree diagram, you'll see it looks like a tree, and it really helps you just map it out, and so you make sure to not miss anything. Okay, so what we're going to have is, first, we're going to work methodically through this list, and we're going to make sure we cover all the different ways this can happen, okay? So let's say in first place, we have Jason, because that's me, right? I'm Jason, and I won, as I'm making the video. All right, and so if Jason wins first place, then obviously he cannot win second place. So if Jason wins first place, he's not going to be, for this particular solution, he's not going to be the second place winner. The only second place people are going to be these leftover people. So we're going to work methodically through it. Let's say that Sean wins the second place, okay? And this would be one permutation, Jason and Sean. But on another day, Jason might have got first place and Sally might have gotten second place. Okay, and on another day, Jason might have gotten first place and Martha might have gotten second place. So we've worked our way through several of these ways it can happen. Jason and Sean is one day, Jason and Sally, Jason and Martha. Okay, now let's continue on. So I won first place, and these guys we're laying out here. Let's continue. Let's say Sean won first place. You can see why it's called a tree diagram. I'm kind of building a tree here, okay? So if Sean wins, then these other people are the only people that can get second place. So first we say Jason wins, then we say Sally wins, then we say Martha wins, okay? Jason, Sally, and Martha, okay? Again, Sean won first place this time, so let's move down and say, let's say Sally won the first place, okay? And if Sally wins, then these guys here are the only people that can get second place. So it would be Jason, Sean, and Martha. All right. And again, we continue building our tree. All right. And then finally, if Sally got first place, now let's go ahead and say Martha actually won the race. And if Martha wins, then these 3 people are the only eligible people to win second place. So it would be Jason, Sean, and Sally. Okay. Congratulations, you've just constructed your first tree diagram. Now you see, if you didn't actually do it in this methodical manner, you'd probably miss one of these orderings, okay? You have Jason and Sean, and Jason and Sally, and Jason and Martha. Sean and Jason, Sean and Sally, Sean and Martha. Sally and Jason, Sally and Sean, Sally and Martha. So, you know, if you just try to just bang these out on your paper and just do your best to list them all, you're going to miss some. But by doing a tree, by picking the first and then listing all the possible seconds, next guy's first, all the possible seconds, and so on, you can do this, okay? So we've done the tree diagram. Now the question we were trying to answer, the actual thing we're doing here, is we're trying to figure out how many ways can this happen. From this race of first and second people, I have 4 people, and I'm only looking at first place and second place. How many different ways can that happen? Well, how many permutations are there in the winners of first and second place? The orderings, basically, is what you're looking at. How many ways can it happen? Well, you just count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So what we have found, so I'm going to put a giant curly brace here. What we have found, 12 outcomes. Okay, 12 outcomes, 12 permutations is what we have found, 12 permutations. Now let me show you something interesting, and then we're going to go and learn about something and make it more mathematically. I haven't even done any math here. We're just counting, really, is all we've done. let me show something to you. We've constructed this tree. What we have found out is that there were 4 different first place finishers. There were 4 different ways in which first place could finish. Okay, and then of every one of these cases for first place, there was 3 people that could possibly win for second place. So there was 1, 2, 3, 4 possible ways first place could win, and for every one of those, there was 3 people that could win second place. So I'm not even proving anything to you. I'm just merely pointing out. Notice 4, which is the number here, 4 times the 3 people for every place, just happens to equal 12. Now, I bet you can guess that I'm not just going to tell you this is a coincidence. This is exactly how we're going to end up solving these problems. I'm just sort of laying the foundation by counting and showing you that you had 12 outcomes, and just so happen to notice that 4 first place finishers, and for every one you had 3 possible second place finishers. 4 times 3 gives you 12. Okay, so I'm showing you by example. Now, the answer is it's not coincidence. It's not coincidence at all. In fact, this is something called the fundamental counting principle. And what we're going to learn about is we're going to learn about that here. So let me go and let's present the fundamental counting principle to you. It's something you'll see in your book usually, your little theorem, and people's eyes glaze over when they see theorems because they have a lot of math jargon in them. Well, I've shown you by example it's not a big deal. Okay, we're going to work through it here. Let me go ahead and go over it with you so you'll be familiar with it. The way the fundamental counting principle works is the follows. Let E1, E2, E3, all the way to EK, K could be K events, okay, be a sequence of events. The first event, E1, can occur M1 different ways, okay? After E1 occurred, E2 can occur M2 different ways. E3, event 3, can occur M3 different ways, and so on, all the way to however many events you have, okay? The total number of ways that all K events can occur, because we had K events, right, is M1 times M2 times M3 times M4, okay? So let me read that one more time, and we're going to apply it to what we learned here, and it's called the fundamental counting principle, okay? We're going to have some events. That's what we had here. We had a first place event, and we had a second place event. Those are our 2 events, E1 and E2 in this case, okay? Let E1, E2, E3, all the way to however many events you want to have. You can have 10 places in your race. The 10th place, the 7th place, you could be looking at different numbers of people finishing the race. E1, E2, E3, all the way to EK, however many events you have. Let them be a sequence of events. The first event, E1, can occur M1 times. The second event can occur M2 times. The third event, M sub 3 times, all the way to however many events you have, M sub K times. The total number of ways that all of these events can occur is going to be M1 times M2 times M3, all the way to M sub K, however many events you have. So, putting it into the context of our specific example, what we have is, okay, this number, okay, event 1, which is, event 1 is how, who crossed the finish line first. Event 1 occurs 4 ways. So in the theorem it says event 1 can occur M1 ways. Well, M1 is 4 because event 1 can occur 4 ways, okay? And what this is saying, okay, is that event 2 occurs 3 ways. Okay? Why does it occur 3 ways? What it's basically saying here is because the order matters, okay? Any race that you finish, once the first person crosses the finish line, like up here, by definition, when that first person crosses, there's only 3 ways in which the next event can happen. So anywhere in this chart, you're looking at the second event that's going on here, that we're talking about, the fundamental counting principle. The second event can only occur 3 ways by definition because you have removed one of those choices from the list. Once Jason crosses the finish line, he's no longer in the running for second place. So, first event can occur 4 different ways. Once the first event is chosen, the second event can only occur 3 different ways. So the fundamental counting principle, if you go back and read the theorem again, you have however many number of events you have. The first event can occur however many ways, M sub 1. The second event can occur however many ways, M sub 2. The fundamental counting principle is if you want to find out the total number of ways in which this thing can happen, the total number of permutations, all you do is you multiply the number of ways the first event can happen times the number of ways the second event can happen. If you have a third event and a fourth event and a fifth event, you just keep multiplying by the number of ways in which those events can happen, okay? So I think that pretty much gets the point across here. So let's go ahead and move over and just continue talking a little bit more about permutations. And we've got the basic idea. You know what it is. Let's continue working with it and work some more problems. Really get comfortable with how to use everything, okay? So we've already talked about the fact that when you have, in this particular example, the number of ways, or each way that the race can finish from first place to second place, this is a permutation. This here, Jason and Sally, is another permutation. Jason and Martha is another permutation. Sean and Jason is another permutation. You go down the list, you have listed the number of permutations that you have. So let me give you a formal definition. I've been talking about it. Let me give you a formal definition for what a permutation is. File it away and remember it, okay? A permutation of n elements, here we had two elements, 1, 1, and 2. Permutation of n elements is an ordering of the n elements such that one element is first, one element is second, one element is third, etc., etc. Okay? So in other words, the ordering does matter. Okay? So let me say that one more time. A permutation of n elements is an ordering of the n elements such that there's a first, a second, a third, and a fourth, and so on and so on. That's what a permutation is. Okay? So just to show you what I'm talking about, the order does matter for permutations. I want you to burn that in your head. Say it 10 times. For permutations, the order matters. For permutations, the order matters. Because later when we get to combinations, it might confuse you if you don't have that memorized. So memorize it. Please do yourself the favor, okay? What we're saying here when the order matters is first place, second place. Jason and Sean is a different permutation than Sean and Jason. You see? It's the same people here, Jason and Sean, and here's Sean and Jason. So one could say, what's the difference between the two? Well, it's obvious from this example because it's a race. If Jason comes in first and Sean comes in second, that is obviously different than Sean coming in first and Jason second. But it is the same people in those events. But the fact is, for permutations, the ordering does matter. So every order you have of the same elements, the elements of the people in this case, leads to a different permutation. When we get to the next section, it's not going to be like that. So that's why I'm trying to point it out over and over again to you, okay? So we've talked about that. So just to drill it in one more time, the rule of thumb is for permutations, if you think you might be dealing with a permutation, you need to ask yourself, does the order matter? If I switch the order of my elements, do I get a different permutation or not? When we do a bunch of examples in the next couple of sections, you'll see what I'm talking about. Sometimes the order doesn't matter at all. We'll get to that in the next section. Okay, so let's work an example. And let's see if we can continue learning about this. Let's list all permutations of the letters in the word cat. Okay? So third grade here, cat. What we want to do is list all the permutations of the letters in the word cat. So you could, we're going to use the math here to figure out how many permutations there are. But let's just go ahead and look at it. I think this has only 3 letters. We could probably do a pretty good job of listing all the permutations. Okay. Obviously, first you have cat. That's one ordering of the letters. Okay. Now, what if I kept C as first place and then I take the last 2 letters and reverse them? C-T-A. Okay. That's a different permutation because it's a different ordering. The order does matter. A different ordering of the same letters leads to a different permutation. Okay. Now, what if C is not first? What if I put A first and then go ahead and put A first and then C and T? And what about A and then TC, just flipping these letters? And then finally, what if I put T first and then go ahead and put CA? And if I put T first and switch these and put AC? Okay, TCA and TAC. I think that's it because I've got C first, A first, and then T first, and every time I did that, I've got the other letters flip-flopped in all the different ways. Study that for a second and make sure that you agree that you believe that's all the different ways these letters can be ordered in that word. Okay, so how many do you have? 1, 2, 3, 4, 5, 6. You have 6 permutations. And by the way, I'm going to start probably shorthanding permutations with perms. You can just think of perms as permutation, okay? All right, so the ordering does matter. The same letters in different order does matter, okay? So let's try to figure out if we can use the fundamental counting principle to calculate this. Here it was short enough for us to write them down, but you may be looking at, the word incredible. How many letters are in the word incredible? Trying to figure out all the different permutations there, you're probably not going to be very successful. So we need to figure out, we're going to use the easy examples to teach you how to do it. Okay, so what we have here, to calculate it here, we have the first letter, the second letter, and the third letter. Okay, so basically this, using the fundamental counting principle language, this is event 1, this is event 2, this is event 3, because if you go back to the fundamental counting principle, I'll just read it for you here. Let E1, E2, E3, etc., all the way to EK be a sequence of events. This is a sequence, you know, it's a letter, it's an event you're looking at. The first event can occur in M1 ways, second event M2 ways, third event M3 ways. The total number of ways in which these can be arranged is just going to be the product M1 times M2 times M3. Well, let me ask you a question. For the first place, the first letter in the word, how many different possibilities do I have there? Well, if I'm going to choose the first letter, I've got 3 letters to choose from. So there's 3 different ways that that first event can happen. That's M sub 1. So it's basically just three ways that can happen. But once I've actually chosen that letter, okay, the first letter here, whatever letter I choose, it doesn't matter if I choose C or A or T, but once I choose it, how many choices do I have for the second letter? I only have 2 choices left because I've chosen the first letter. No matter what letter I pick here, once I choose it, I only have 2 choices for the second letter, okay? All right, now once I choose that second letter, no matter what letter I pick, how many choices do I have for the third letter? Well, there's only going to be 1 choice left. If I pick any one of these permutations here, you know, I had 3 choices for the first one, okay? A T was chosen, so I cover them up. How many choices did I have for the second? Well, I could choose C or A. Well, now I choose C. So for any time I go down there, now that I've chosen C and T, I only had 1 choice at the end. Every time you do that, you're only going to have 1 choice every time you go down. You had 3 choices to begin with, in either of the 3 letters. Once you chose that first one, you only had 2 choices for the second one. Once you chose the second one, you only had 1 choice for the third one. Fundamental counting principle says these different guys should be multiplied together. 3 times 2 times 1, I think you know, is 6. And that's why there's 6 permutations. So what I'm trying to drill into you here is that the fundamental counting principle is telling you that all you need to do if you're trying to figure out the number of ways something can be ordered is to look at how many ways the first event can happen, okay, just like in our race, and then once that's chosen, go ahead and figure out how many ways the second one can happen, how many ways the third one, the fourth one, the fifth one, the sixth one, and you're multiplying them all together. And when you do the multiplication, that is giving you the answer of how many different ways the entire thing can occur as a whole. That's what it's doing, okay? So now what I'm going to do is introduce something you've probably seen in your book. I haven't shown you yet, but it's really doing exactly the same thing as what we've been doing with the fundamental counting principle. Let's go ahead and dive into it. What you are definitely going to see 100% beyond a shadow of a doubt in your book is going to be called something little n, big P, and little n. Okay, and this is a little notation that stands for permutation. The P means permutation, and the N on either side of the P just means, let me just go ahead and write it down here. What this means is it's the number of permutations, that's what you're trying to calculate with NPN. Number of permutations of N things taken in at a time. Okay, in at a time. All right, so what you're going to find in your book, some books present this to you, some books don't. I'm going to do it my way and show you this, and then we're going to get to NPR, which you'll also see in your books. NPN is just simply defined as n factorial. That's what the exclamation point means, n factorial, okay? By the way, just in case, just to make sure everybody's on the same footing, factorial, it looks like a crazy little math symbol. All it means is, let's say you had 4 factorial, okay? All that means is it's 4 times 3 times 2 times 1, okay? When you see factorial, all it means is you take the number and you multiply by every number under it. If you had, you know, 6 factorial, that would be 6 times 5 times 4 times 3 times 2 times 1. That's all it means. Factorial, you take the number and you keep multiplying down till you get to 1. That's all factorial means. You're going to see this running around your book and your class forever and ever, so just get used to seeing it. Every time you see it, you got to remember it's a long multiplication of events, okay? So, what does this mean? Let's look at this. Number of permutations of n things taken in at a time, okay? What I'm trying to say here is, in this particular example, we had 3 letters in the word cat, okay? And what the problem asked was list all the permutations of the letters in the word cat. So I had 3 letters, and I'm looking at the permutations of all 3 letters, okay? So it's in letters, looking at the permutations taken in at a time. In other words, 3 letters looking at the permutation of all 3 letters, okay? Just to show you why this may not always be the case, we'll get to it in a minute. What if I had 3 letters in cat, but I only wanted to look at the order, the number of ways in which only 2 of the 3 letters could be ordered, okay? That would be in things taken, or it would be 3 things taken 2 at a time. So in this example, I'm telling you to find the number of ways in which the letters in the word cat can be rearranged. I'm looking at all 3 letters. So I have 3 elements, 3 letters, and I'm looking at all 3, trying to list the different ways in which all 3 can be reordered. That's why the ends are the same number here. 3 things taken 3 at a time for this particular example. Just backing up briefly, I'm going to get into this in a lot more detail in a minute, but while I have you, in this example here, for the race, I had 4 elements, but I wasn't looking at the ordering of all 4. I only cared about first place and second place. So I had 4 people. You know there's always going to be 4 finishers in a race, first, second, third, fourth, or first, second, third, fourth. You're always going to have first place, second place, third place, fourth place. But for this problem, I didn't care about all 4 people. I had 4 things taken 2 at a time because only first and second place. And I was looking at all the different permutations of only the first and second place finishers, basically. So, getting back to where I was at, when you see NPN, it just means n elements taken in at a time. So 3 letters taken 3 at a time. I'm looking at all the different ways that that happens. When you see this notation, what I'm telling you is NPN is equal to n factorial. So you could look at this problem, okay, now that you know this, and you could look at it and you could say, okay, I'm trying to find the permutations. I've got 3 letters. I'm taking all 3 of them and trying to find the way in which they would go. So if you didn't want to use the fundamental counting principle, you could just go back and look at this and say, well, I'm trying to find the number of permutations of 3 things taken 3 at a time. So n is equal to 3. So I would do 3 factorial. 3 times 2 times 1 gives me 6. Notice it gives you exactly the same thing as the fundamental counting principle we were doing. So I'm going to draw a conclusion here that I want you to remember, okay? When you see in your book NPN, later on you'll see NPR permutations. You'll see that one for sure in your book, okay? All that stuff is doing is exactly the same thing as the fundamental counting principle that I've been teaching you about, okay? We're going to do a lot of examples and show you. But that NPN, NPR, all that's doing is a shorthand way. This is just a shorthand way of telling you 3 times 2 times 1. That's what I was doing. The first event can happen 3 ways. Second event can happen 2 ways. Third event can happen 1 way. 3 factorial is what this is telling me, okay? Later on, when we get to NPR, you'll have a different formula that we'll talk about, and that thing is doing, again, exactly the same thing as the fundamental counting principle. So let's go ahead and continue talking about this, work a couple more examples, and then we'll dive into the bulk of our examples and continue getting really good at this. Okay, the next problem goes something like this, and we'll continue building on what we've done, and we'll forge a little new ground as well. You have 20 people in an election, 20 candidates, okay? How many different ways can you choose a president, a vice president, and a secretary, okay? So what you have here is 20 eligible people, you know, in a list on the ballot, and you're only going to pick first, second, third place, basically, president, vice president, and secretary. So there's 3 winners, basically, first, second, third place, kind of like our race, okay? And I'm trying to figure out how many different ways can that happen. So let's go ahead and calculate it and relate it back to our permutations and all of that. Now, we could construct a tree diagram. I mean, I could list all the names, and then I could list the president, and then all the possible vice presidents, and then all the possible secretaries, and I would have a very big tree because I have president, vice president, and secretary. I could count them all up, and that would be the answer. But the whole point of this is to be able to calculate it without writing all the stuff down every time. I mean, obviously, you can't do that every single time. So let's go ahead and use the fundamental counting principle because we know that we have 3 events. Event 1 is president, okay? That's what we're choosing first. Event 2 is the vice president. That's what we're choosing second. And event 3 is the secretary. Okay? So we have the president, vice president, and secretary. Okay, we have 20 people, okay, that we can choose from, 20 people. So how many ways can you choose president if you have 20 people to choose from? Well, I can have 20 ways to choose the president, okay? Now, I've made a choice. I've chosen my particular candidate for president. How many choices do I have left for vice president? Well, I only have 19 ways that I can choose the vice president, okay? But now that I've chosen the vice president out of 20 people, how many ways can I choose a secretary? Well, I only have 18 choices left, so there's 18 different ways that I can choose a secretary. So I have 20 ways for the first guy, 19 ways for the second guy, 18 ways for the third person, and that's because after I chose the first one, I only had 19 choices left, and after I chose him, I only had 18 choices left. The fundamental counting principle, and I'll just go back and read it, verbatim just to reinforce it. You have E1, E2, E3, and so on, events. This is event 1, this is event 2, and this is event 3, okay? Event 1 can happen M1 ways, and this way we said it's 20 ways. Event 2 can happen M sub 2 ways. Here we're saying it's 19 ways. Event 3 can happen 18 ways, M sub 3. The fundamental counting principle says that the number of ways in which the whole thing can happen is 20 times 19 times 18. Okay, and when you do that, you will see that that's 6,840 ways. And since the order does matter, that's what we're talking about, an election here, these are called permutations. Okay, so 6,840 permutations is another way of saying the same thing. So what we're saying here, we're using the fundamental counting principle. This many ways for the second candidate, this many ways for the third. You multiply them together, you get the answer. That's the number of permutations that you have, okay? Now, I just want to prove to you, notice that the order did matter, because if, for instance, if I had, here's the president, here's the VP, and here's the secretary, okay? Let's say person A picked, let's say, Mark for the president. Let's say they pick Jane for the vice president, and let's say they pick Sarah for the secretary. That is one permutation of the way in which the things can be ordered, okay? But if I turn it around and say, okay, Sarah, someone else picked Sarah, and that other person picked Jane for the vice president again, and then picked Mark for the secretary, okay? They're the same people involved. This listing of people is the exact same listing, the exact same people as in the second listing here, but these are different permutations. These are different permutations because the order is different. I keep beating it into your head over and over again. For permutations, the order is always different. The order matters is another way you'll see it written in the books. Anytime you have first place, second place, third place, anytime you have a race, anytime you have vice president, president, treasurer, anything that you can just think about for a second and say, well, look, if I switch the order of people, the permutation is going to be different. The socks on my bed, red, yellow, and then green. Okay, now I switch them. Green, and then red, and then yellow. Those are different ordering. So it's a different ordering, and if I'm looking at it in terms of trying to pick different orders of socks on my bed, those are going to be different permutations. So that's what we're trying to say here. Now let me introduce something I hinted about just a minute ago. You will see this in your book. If you have permutations, of n elements taken r at a time, okay, n elements taken r at a time. Yeah, I'm going to underline the word taken. I'm going to come back to that in a second, but they're n elements taken r at a time. This is a little different than what we had last time. Then what you will see in your book is n, little n, big P, little r. Let me write it down. We'll talk about it. It's defined as n factorial over n minus r factorial. That's what it's defined as, okay? So, before you get too scared of this formula, this is doing exactly the same thing as the fundamental counting principle. We were doing the fundamental counting principle here. We were saying the first thing can happen 20 ways, the next thing can happen 19 ways, the third thing can happen 18 ways. This formula is doing exactly what we did there. It's just in a kind of a more obscure notation, okay? How would we apply this, okay? If we were going to apply the problem we just solved to that, what we're saying here in our election is we had 20 candidates, so we had n things, n elements taken r at a time. R is different than n because the number r, when you're using this formula, is not going to be the same as the number n. So you have 20 elements taken 3 at a time because we're actually only looking at 3 different people at once. Basically, those are the different number of elements we're looking at any given time. So the way you would write that down is you would say 20p3. N is 20 because I have 20 elements, p for permutation, and I'm looking 3 at a time because I only have 3 places here in my list. That's all I care about. Okay, so since n is 20, you have 20 factorial, n factorial, and on the bottom you're going to have 20 minus 3 factorial. So now it's just math, okay? So let me simplify this a little bit. 20 factorial over 20 minus 3 is 17 factorial. Now, once you get to this step, you can do a few things. You can put 20 factorial in your calculator and you can calculate a big, big number on the top, because what does this mean, by the way? 20 factorial is 20 times 19 times 18 times 17 times 16 all the way down to times 1. So it's going to be a very big number. On the bottom, 17 factorial is 17 times 16 times 15 times 14 all the way down to times 1. So it's again a very big number. You can multiply them by hand and then you can divide. You can put 20 factorial on your calculator and get a big number, top and bottom, and you can divide. But I'm going to show you something because you really need to learn this. It'll really help you out a lot. Okay, let me show you something real quick. I'm only going to do this probably one time, but I do want to give you the hang of it here. What is 20 factorial? Just write it out. 20 times 19 times 18 times 17 times 16 times 15. Now I don't have enough room, so I'm going to write times ... times 1. That's what 20 factorial is on the top. All of this stuff is divided by 17 factorial, which is 17 times 16 times 15, again, times ... all the way down to 1. Now, think back to algebra or basic math or whatever. You have a bunch of stuff multiplied together, and you have a bunch of stuff multiplied on the bottom. The 17 is going to cancel with the 17, the 16 cancels with the 16, the 15 with the 15, the 14, 13, 12, all the way down. The 1 is going to cancel with the 1. So basically, everything from here on actually cancels out. So in the end, all you're going to have is 20 times 19 times 18. Okay? So you have 20 times 19 times 18. When we calculated that before, that's 6840. Now look at what we did here. I told you that this formula that you'll see in the book, and a lot of people shudder when they look at it, oh, permutations, it looks so complicated, okay? You put the stuff in, look what happened. The 20 on the top and the 17 on the bottom, most of it ended up actually canceling. All I was left with was 20 times 19 times 18. This gave me the answer. Now go back up here. That's exactly the same math that we actually did up here using the fundamental counting principle. So what I'm trying to drill in is that when you're using the permutation formulas, okay, when you have a problem, when you're using the permutation formulas and you're actually that's why it says when it's taken, n elements taken are at a time. This case, when we're doing a first place, second place, third place, or a presidential race where you have first place, second place, third place effectively, after you remove the first element, you have less elements left to choose from. Those kinds of problems, you can use these formulas, okay? In those cases, when you're applying n elements taken r at a time, or n elements even taken n at a time, the math that you do when you put n factorial, n minus r factorial, gives you the exact same thing as if you had just used the fundamental counting principle. So really, I prefer to start teaching the fundamental counting principle first, just so you can kind of see what that is, and then this whole permutation formula thing isn't become such a big deal. They're all doing the same thing. It's just that this, for instance, might be much more easy to use in a computer. You might be able to program a computer to do this a lot better than teach it how to use the fundamental counting principle. But both things are done in exactly the same way. All right. Now there is one more thing I want to show you, and then what we're going to do after that, we're going to erase the board and we're going to do a whole lot of problems to get you comfortable. Okay. On the previous board, I told you permutations of n elements taken n at a time. When I was looking at all the elements, like for cat, 3 elements taken 3 at a time. We're looking at all the different permutations of all 3 things, which is different than here when we have 20 elements and we're only looking at 3. Okay. We said that npn was equal to something, okay? Well, let's put it in here just for kicks. N, P, N. Let's use the more general formula. You're going to have n factorial on the top, because that's what n is equal to, but r, basically I'm telling you, just to prove it to you, r is equal to n. So let's go ahead and put it into this. In the bottom you have n minus n factorial on the bottom. Here all I'm doing is I'm saying r is equal to n. Let's see what you get. Then on the top you'll have n factorial. On the bottom, n minus n is 0 factorial. And you may or may not remember this, but back from your algebra or whatever class you first learned about factorials, 0 factorial, believe it or not, I know it sounds a little bit odd, it's always defined to be 1. Okay, that may actually stop you in your tracks and you might say, why is it equal to 1? Well, my advice to you is, don't worry about it. And I hated it when people told me, don't worry about it. But what I'm telling you is that in math, certain things are defined, okay? And by definition, certain things are defined to be a certain way and you build upon them. Factorial is, 5 factorial, 5 times 4 times 3 times 2 times 1. So 0 factorial just doesn't seem to make much sense that it would actually be equal to 1. But it's a definition. It's not something that you prove. It's something that was written down as a definition. That's what you use because it's a definition. So 0 factorial is 1. So what you have from all of this, getting back to what I was talking about, is just n factorial. That is exactly what I told you on the previous board. So I'm trying to show you that these are not different. These are not different formulas. Some people try to memorize this. NPN is equal to n factorial. Oh my goodness, I have to memorize that. And then this one is equal to this. I have to memorize that. What I'm telling you is they're the same thing. If you just want to remember this, fine, because it's always going to work. This is a special case. This is a special case when I have n elements and I'm looking at the orderings of all n elements. 3 letters in the word cat. I'm looking at all the different ways those 3 letters can be rearranged. Here I've got 20 elements, 20 candidates on the ballot, but I'm only looking at the different ways in which 3 of them can be arranged. That's why this is the more general formula. Okay? So let's go ahead and work through some problems. We're going to do quite a few of them, and we'll see when we can just apply the fundamental counting principle and when it's okay to apply this, and we'll get practice and we'll get good at these things. Okay, the first problem goes something like this. You have a 7-digit phone number, okay, the regular phone number, 7 digits, and in a particular city, the first 3 digits always begin with 661, okay, just a specific pattern, 661, the first 3 digits. How many different numbers, how many different phone numbers, how many unique phone numbers are possible in that city, given that the first 3 of them always start with 661, okay? So what we have to first think about is what kind of problem is this? I told you every problem in probability is a word problem, okay? So this is a word problem. You have to know what it's asking you before you can do anything. So you're dealing with a phone number and you're dealing with ordering of something. So the first thing you need to ask yourself is, does the order matter? If so, it's a permutation problem. So it's a phone number. And if you look at phone numbers, I mean, if you just think about it, okay, the number 661, because we said all these phone numbers begin with 661, 661, 0, 1, 2, 3. And if you look at a different number, 661, let's look at, 1023, same numbers, but different order. Obviously, these are different phone numbers, okay? So what you learn is, by switching the order, it leads to a different phone number. So the order does matter, okay? So this is a problem in permutations. So I just need to start thinking about my permutation rules, okay? So first thing I want to look at when you're dealing with these permutation things, the first thing you always want to think about is, can I use the fundamental counting principle? Okay, can I use the fundamental counting principle? So draw yourself a little picture. You have the first digit, the second digit, the third digit, and the fourth digit. Now this problem was set up to be a little bit tricky because I told you the first 3 numbers are always 661. So these numbers actually don't have anything to do with the answer because the question said, how many different numbers are possible? Well, the first 3 digits are always the same. So only the last 4 are the ones that are allowed to change, and so only the last 4 are going to be the ones that tell you how many different numbers are possible. So you have to think about it and realize that, okay, these are fixed, so they don't have anything to do with anything. Only the last numbers will yield different permutations, okay, because those are the only ones that can change. All right, so this digit and this one and this one and this one represent the last 4 digits of the number, okay? So this is the 4th digit, this is the 5th digit, this is the 6th digit, and this is the 7th digit. Okay, now my question to you is, looking at the fundamental counting principle, I have 4 elements, element 1, 2, 3, and 4, okay? And each one can occur at however many ways, and I'm trying to calculate how many I have total. How many ways can this digit be chosen? Well, there's 10 digits on a phone, right? 0 through 9. You have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 digits on a phone. So this number can be chosen 10 different ways. Okay? Now, how many ways in which the second number can be chosen? Well, again, I have 0 through 9 I can choose for him, so I have 10 here. I can choose this 10 different ways for this digit, and I can choose this 10 different ways for this digit. So the fundamental counting principle is I have 4 events. This event can happen this many ways, this one can happen this many ways, and so on. So all I do is I multiply them all together, and what you will get is 10,000 ways, also called permutations. 10,000 permutations, okay? And all we did was we looked at the fundamental counting principle. We said, look, this digit can occur this many ways, and so on, and so on, and so on. Once I know how many different ways everything can happen, I just multiply them together, and that's what I do. Now, one thing I want to point out to you, because it really is important that you think about this. Early on, students might say, why can't I just use the permutation formula, the NPN, okay, or the NPR, or whatever? You could ask yourself, why can't I just do that? Okay. Well, the reason is because if you look at the way I wrote that, the definition says n elements taken are at a time. Okay. That means that, you know, in those problems, if you looked at it, in those problems, we were always dealing with first place, second place, third place. Okay. You have so many that you're looking at, you remove somebody from the pool, and then you have less people for the second one. And then you pick that one, you remove him from the pool, and you have less people. So all the permutation formulas, NPN, NPR, whatever, they're all written in terms of n elements taken are at a time. Here, nothing was actually taken. I have 10 ways in which this can happen, 10 ways in which this can happen, 10 ways in which this can happen, 10 ways in which this can happen. The problem just sort of tells you that you're actually not taking anything away from it, so you don't use the NPR formula here. Just use the fundamental counting principle. So, and we did that very easily. It was very simple math. So my advice to you is, for every problem that you think is a permutation problem, try to figure it out with the fundamental counting principle, because it's pretty easy to do. Try that first, and for whatever reason, if you don't want to do that, or if you're confident you can use the NPR formulas that we'll get to in some other problems in a minute, then go ahead and use that one. But make sure that in those problems where you're using NPR, you have to have a specific ordering, first place, second place, third place, something like that to make it work out, okay? Let's go on and go to the next problem. It's a very similar problem with a twist, okay? How many different 4-letter radio station call letters can be arranged if the first letter must be W or K, and the letters may be repeated? So, you know, you might just listen to the radio and you know, you might hear WKRP or something, the call letters of the radio, or WPPJ for the letters, okay? So what we're saying here is we have 4 letters that were call letters on the radio, but it's very similar to this problem that we had before, except there's a twist. How many different 4-letter radio station call letters can be arranged if the first letter has to be W or K, and the letters can be repeated, okay? So we need to ask ourselves, do we think this is a permutation problem or not? Well, when you think about it, WKRP is a different permutation than PWQR, okay? I mean, you know, the different letters of the call, if you're using the same letters and you change the order of them, it's a different permutation. So this problem is a problem in permutation, so let's go ahead and see if we can figure it out. Let's go through our list and see if we can do the fundamental counting principle. So what you have is the first letter, they have the second letter, you have the third letter, and you have the fourth letter. Okay, 4 letters, 1, 2, 3, and 4. The only thing that I was told is that the first letter has to be W or K, and the letters can be repeated. So I ask you this. How many different, this is event 1, event 2, event 3, and event 4, if we're going to use the fundamental counting principle. How many different ways can the first letter be chosen? Well, I was told the first letter has to be W or K, so there's only 2 ways in which the first letter can be chosen. And the letters can be repeated, so how many different ways can the second letter be chosen? Well, there's 26 letters in the alphabet, and the letters can be repeated, so there's 26 ways in which that can happen. How many different ways can I choose this one? Again, 26 ways. How many different ways can I choose this one? Again, 26 ways. Event 1 can happen 2 ways. Event 2 can happen 26 ways. 3 can happen 26 ways. Event 4, 26 ways. So the fundamental counting principle says, once I know how many different ways everything can happen, I just multiply them together. So what we have at the end is 35,152 ways, which are called permutations, okay? The reason they're called permutations is because for this problem, just by the nature of the problem, different ordering of the letters is going to yield a different radio station identifier, okay? So again, I want to drill it in again because we're going to get some problems that are not quite the same, not quite hold true. But in this problem, nothing was actually taken. There wasn't really there is a first place, second place, third place, as far as the letters, but it's not like a race where you have somebody, it's not like a race where you have somebody win and then he's removed from the pool, and then you have less people to choose for the second one. Because the letters can be repeated, you see. So it's not like a letter is removed and I can't pick him anymore. In problems like that, it's okay to use the NPR formula, okay? But in this problem, you really can't use that formula, NPR, because nothing was taken. Those formulas are written in terms of problems that you have n elements taken r at a time. Well, nothing's really taken here. I have so many choices each time, multiply them together, that's the way it goes. So I always recommend, if you think it's a permutation, work through the fundamental counting principle first, and then if you decide not to do that, or if you want to use or if the teacher tells you, use the permutation formulas, then you'll have to apply it appropriately, okay? So let's go ahead and work another problem right under it. The next problem says, how many 4-digit odd numbers greater than 3,000 can be formed using the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, if the digits may be repeated, okay? So half the battle here is just knowing what to do, okay? You have a 4-digit number, but there's a lot of constraints on it, and we're trying to figure out how many different ways in which these numbers can be ordered, okay? So it's a 4-digit number, very similar to the 4-digit call sign from before. How many ways can you arrange 4-digit number, but it's an odd number greater than 3,000, and you can use all the digits 0 through 9. So how do we do that? I always like to draw a picture, even though it's the same picture every time. First digit, second digit, third digit, fourth digit. First digit, second digit, third digit, and fourth digit. Okay? How many ways? We're going to use the fundamental counting principle. This is our first event, second event, third event, fourth event. Ask yourself, how many ways can this first one occur? Well, notice that the numbers we're allowed to use in the problems is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We know this, okay? Okay, so how many different ways can I choose this first digit here? The problem says it's a 4-digit number, but it's greater than 3,000. Okay, these are the digits I'm allowed to choose from. I can't pick 0 for the first because it's got to be greater than 3,000. I can't pick 1. I can't pick 2. I can pick 3 because this could be 3,124. That's greater than 3,000. 3,596. That's greater than 3,000. So I can pick 3 through 9 for my first digit. So that's 1 choice, 2, 3, 4, 5, 6, 7 choices. Okay, 7 ways. I can pick the first digit 7 ways because the number has to be greater than 3,000. How many ways can I pick the second digit? Well, it really doesn't matter what I pick here. I can have 10 choices, 0 through 9. Okay? It doesn't matter here what I pick for the third digit. I have 10 choices here. But for the fourth digit, the problem also says it has to be greater than 3,000. And it's an odd number. It's an odd number. Okay? The odd number means basically that the number has to end in 1, 3, 5, 7, or 9. It can't end in an even number. I mean, that's exactly what odd numbers are, right? So this is constrained. The last digit's constrained, okay? He can end in 1, 3, 5, 7, or 9. So how many choices? 1, 2, 3, 4, 5 choices. 5 choices for the last digit. So now I know how many different ways everything can happen. I just multiply them together, and what I get is 3,500 ways, which are also called permutations. Okay, it's the same thing, 3,500 permutations. Okay, so the first digit, the problem says how many 4-digit odd numbers greater than 3,000 can be formed using digits 0 through 9. First digit's constrained can only happen 7 ways because I can pick digits 3 through 9. I can't pick these other ones, so it can happen 7 ways. These two here can be any number of digits. It really doesn't matter, but because it's an odd number, this digit can only happen in 5 different ways because it's an odd number. I multiply them all together and I get 3,500 ways. Now you can see why you would not use this tree diagram every time. You could create a tree diagram for this like we did for the first problem, but there's no way you're going to get 3,500 choices and get them all. So you have to know to use the fundamental counting principle. Now the other thing I want to point out, just like I did for the last one, is these elements, element 1, 2, 3, and 4 that you're choosing here, students might look at this and say, well, why don't I just use the permutation formula? Well, the permutation formula says in elements taken are at a time. Taken meaning just like the vice president, president. You take a candidate, pick him, he's removed, and you have now less people in the pool to choose from. This problem doesn't fit that mold. You have this many ways, and so on, but you really haven't removed anything because the numbers can be repeated. All of the numbers are really available for the second and third choices, and digits can be repeated, so you really haven't taken quote-unquote anything away. So you don't use the NPR formula for this, you just use the fundamental counting principle. Okay, so let's go on and do another problem and continue getting practice. Okay, the next problem says, in how many ways can 10 people finish a race in first, second, and third place, assuming you don't have any ties? Okay, so again, this is a problem you need to read, just make sure you understand it. In how many ways can 10 people finish a race, but we're only looking at first, second, and third place. We're not looking at all 10 places. We're looking at only first, second, and third place. How many ways can that happen, assuming you don't have any ties? So the first thing you need to do is look at this and say, is it a permutation problem? Well, obviously it's a race. I keep trying to tell you, if you see first, second, third places where you have definite orders, it's definitely a problem in permutations. So it's a permutation problem, okay? In permutations, the first thing I always tell you to do is try to see if you can use the fundamental counting principle. So let's try that first and see what we find, okay? So, because it's a race, you have first place, you have second place, and you have third place. Okay? First, second, third, that's all we're looking for. 10 people are in the race, okay, we know that. So let's ask ourselves, how many different ways can event 1 happen? This is event 1, 2, and 3. How many different ways can first place be chosen? Well, there's 10 ways to choose the first place winner. Once the first place winner is chosen, that person, whoever it is removed from the pool, and you only have 9 choices left for second place. So second place can only happen in 9 ways. Once second place is picked, those 2 people, first and second place, they're both removed from the pool, and you only have 8 ways in which third place can happen for any given combination. So the fundamental counting principle says you just multiply these. 10 times 9 times 8. And what you will have is 720 ways, which are also called permutations. I'm just giving you, different things to think about as far as the terms. 720 permutations, that's the answer. Now, that's the fundamental counting principle. I find it very easy to think about 10 ways, then you have 1 less 9 ways, 1 less 8 ways. Okay, fine. You get 720 permutations in the answer. But let's ask ourselves, can we use the permutation formula? In this particular case, you can. NPR, let's write it down. What it was equal to is n factorial over n minus r parentheses factorial. Why can we use this in this problem and we couldn't use it in the other problems? Because the permutation definition says you have n elements, okay, taken r at a time. And in this case, the word taken is very important because once you choose the first element, he's taken out, and then you choose the second element, he's taken out, they're removed from the pool. Those kinds of problems is what you are really allowed to use this formula for, okay? And that button on your calculator that you see, NPR, these are the only kinds of problems you can do, okay? So I have 10 people taken, this is how you would read it, 3 at a time. Ten people taken 3 at a time. That's what n and r is. So n is equal to 10, r is equal to 3, and that's how you would apply it in this formula. So n factorial is 10 factorial, and on the bottom you'll have 10 minus 3 factorial. All right, so what you would have is 10 factorial on the bottom, 10 minus 3 is 7 factorial. Now you could punch 10 factorial in your calculator, and you could put 7 factorial in your calculator, and you could divide the numbers and get the answer. But it's real instructive to look and say, well, 10 factorial is 10 times 9 times 8 times 7 times 6, 5, 4, 3, 2, 1, okay? And on the bottom is just 7 times 6, 5, 4, 3, 2, 1, okay? Now, because I'm dividing just like before, the 7s go out. Basically, all this stuff cancels with all this stuff down here. So really, all you're going to be left with is 10 times 9 times 8, which we already talked about is 720. So look at what we've done here. We use the fundamental counting principle because we know how many different ways everything can happen. We multiply them together. When we use the actual permutation formula, what it reduces to is exactly the same thing that we got before. So again, I'm drilling in the point. When you use the permutation formula, you were doing exactly the same thing as the fundamental counting principle. So I just recommend that you just start with that first. Start with the fundamental counting principle and see if you can go ahead and do it. If your test says that you have to use the permutation formula or something like that nature, then you can go ahead and use it and you'll know how to use it, but it's really doing the same thing. Okay? So the next problem says, in how many ways can 6 paintings be displayed in each of 6 different places in a row on the wall of a museum? Okay, so let me read it again, just make sure and soak it in and make sure you understand what it says. In how many ways can 6 paintings be displayed in each of 6 different locations in a row on the wall of a museum? So you have a wall in front of you. You have 6 paintings, 1, 2, 3, 4, 5, 6. How many different ways can these 6 paintings be arranged or rearranged? That's really what it's saying here. How many different ways in which that can happen? Okay. So what you need to look at, you know, if you were going to do this, you would say, I have one painting, another painting, another painting, another painting, another painting, another painting. 1, 2, 3, 4, 5. This is 6 paintings. These things are literally paintings. Okay. All right. So again, you could use the fundamental counting principle. How many ways can I choose the first painting? Well, there's 6 paintings, so I have 6 choices. But once I choose that painting, he's removed, I only have 5 choices left for the next one. Once those are chosen, I only have 4 choices, and then 3 choices and 2 choices, and once I choose these guys, I only have 1 left. So basically, you can multiply all these together with the fundamental counting principle and figure out what the answer is, and the answer is 720 ways. Okay, 720 ways. Okay, now can you use the permutation formula? Yes, you can. Okay, the reason why is because if you're trying to use NP R, okay, n elements taken R at a time, what you're saying is, in order to know if you can use that or not, you have 6 elements, but you're actually, as you select them down, you're actually taking them out and throwing them away, and you have less and less things to look at as far as your arrangements go. So you actually take them away, and that's what allows you to use them. These are different than the phone number problems where things can be repeated. These guys, once you take one painting out, he's gone, and you have only you have less paintings to look at. So you can use this thing. The general formula for this is n factorial over n minus r all factorial. Okay, I have n elements, okay, 6 elements, and because I'm looking at all 6 of them in the arrangements, they're taken 6 at a time. Okay, 6 elements taken 6 at a time. You know, that's a little bit different than this one over here, just to kind of give you the contrast. Where we were doing this problem over here, we had 10 elements, 10 people, but we're only looking at 3 of them at a time, getting our orderings right here with 3 of them at a time. We're only looking there, so it's 10p3. Here we have 6 paintings, but we're looking at the order of all 6 of them, so it's 6 elements taken 6 at a time. So it's 6 elements taken 6 at a time, so it's 6 factorial, and on the bottom it's 6 minus 6 factorial, okay? So on the top you have 6 factorial, the bottom you have 0 factorial. So it's 6 factorial, remember 0 factorial is defined to be 1, so you have 6 factorial, and you should remember 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, and we've already said that's 720. Okay, so both methods lead to the exact same result. If you use the fundamental counting principle and just sort of think about it, you can get it. If that doesn't come to you and you just want to use this, I have 6 elements. I'm looking at the arrangement of all 6. Choose n and r, plug it in the formula, and you will get the right answer there. Okay, now the final problem we're going to do in this section says, how many arrangements can be made using 3 of the letters in the word dolphin if no letter is repeated? Okay, so you have the word dolphin. The word dolphin has 7 letters in it, but I'm not looking at all 7 letters. I'm only looking at 3 at a time, so I have 7 elements taken 3 at a time, and I'm trying to figure out how many different permutations there are if no letters can be repeated, okay? So the first thing you need to ask yourself is, does the order matter? Is this a permutation problem at all? And yes, the order does matter because you're trying to figure out how many different ways you can arrange the letters. You have the same letters, but if you have the same letters in a different order, it's a different permutation for this kind of problem, so it is a problem in permutations. Okay, let's go ahead and dive straight into using the NPR formula and see if that makes sense, okay? Now let's just go ahead and use it that way. What you have is the word dolphin. Okay, 1, 2, 3, 4, 5, 6, 7 letters. So what you have is, if you want to write it down, 7 letters taken 3 at a time. And because once the letter is taken, no letters are allowed to be repeated. That's what the problem says. They actually literally are taken and they're removed from the pool of letters that you can pick. So you can use NPR because you have to actually take the elements away in order to even be able to use this thing. So it's n factorial over n minus r factorial. In this case, n is 7 because I have 7 elements, and on the bottom r is 3, so it's 7 minus 3 factorial because I'm taking them 3 at a time. So on the top I'll have 7 factorial, on the bottom 7 minus 3 is 4 factorial. Again, you could calculate the factorial on the top and the bottom, but it's just as easy to say 7 times 6 times 5 times 4 times 3 times 2 times 1, and on the bottom it's just 4 times 3 times 2 times 1. So all of these numbers cancel with all of these numbers, and then when you take 7 times 6 times 5 and put it in your calculator, what you will get is 210 ways, which are the permutations. Okay, 210 ways. So all we did, we said we had 7 elements taken 3 at a time. They really and truly are taken out because no letters are allowed to be repeated. It's a problem in permutation, so I'll go ahead and apply the formula, plug it in, cancel where you need to, and you'll get 210 ways. Now, if you didn't want to do this first and you were just going to look at the fundamental counting principle, the first thing you would do, because you have 7 letters available, but you're only you're only looking at how many ways in which 3 of the letters can be arranged, what you would write down is, if you're going to use the fundamental counting principle, is you would say, well, for the first digit, I can arrange it 7 ways. Because if I'm going to pick any letter in the word, I have 7 choices. Dolphin has 7 letters. For the second letter, I would have 6 choices. And for the third letter, I would have 5 choices. So if I were going to use the fundamental counting principle from the start, I would start out by saying, well, my first digit, I have 7 choices. Once he's chosen, I throw him away and I have 6 choices left for the next one, and then I have 5 choices left for the next one. I stop there because I'm only looking at 3 letters. I do this multiplication, I get the answer, 210. It's the same thing. Whether or not you use NPR, whether or not you use the fundamental counting principle, it is the same thing. So in this section, we've covered some incredibly important material, the topic of permutations. It's our first introductory section in the whole class. I hope it was clear for you. I plan to make the whole course this clear, okay? The thing you need to remember about permutations is the order matters. If there's one thing you have to remember from this section, and only one, it would be that permutations, the order does matter. Because in the next section, combinations, you'll find the order doesn't matter, and that's what really gets people confused. When you talk about, is it a permutation or is it a combination? The key is the order matters. So in all these examples, when you go back and look at them, you should be able to convince yourself that in every single case, if you were to take one of the answers and flip the order of something based on the problem that was given, it would be a different valid way in which that thing can be arranged. So that's why those are problems in permutations. Okay? You can always use the fundamental counting principle for permutation problems, usually anyway, and you just start out, look at how many ways the first thing can be arranged, times how many ways the second, times how many ways the third, how many ways the fourth, and on. You keep multiplying and get the answer. And for certain problems where you actually do take the elements away, in these places with first, second, third place, or when you're actually taking letters of the word and you're not repeating letters, you can actually use the NPR formula to do the very same thing. But even in that case, it's actually doing exactly the same math as the fundamental counting principle. So try not to get confused there. It's doing the very same thing. So let's go ahead and close now. Practice your problems, do lots and lots of problems, and I think you'll be very good with doing permutations in statistics and probability.